Okay, so we have been introducing p-MOSFET as a separate complementary device, but I mean the question that that we should ask ourselves is, how does it help? How does it help in our situation? So let's go back to the requirement. Then we will then let's see whether a p-MOSFET can help us or not. What was the requirement? The requirement was, we wanted this terminal, right? V naught, whatever is connected to V naught from the top should be the drain. Now, in case of an N MOSFET, the lower potential terminal is always a source potential, right? However, note that in this new device, which is the source potential, which is the source terminal, the higher potential terminal is the source terminal, right? So in a p MOSFET, so let's make the distinction. So this is N MOSFET, this p MOSFET. So to turn on, so let's write it in this way. If VGS is greater than equal to threshold voltage MOSFET is on, right? So instead of writing MOSFET, what I will write is, I will always call this, let's call this M1. M1 is on, correct? What else we know? We also know that higher voltage terminal between, let's say I call this G, this is A, between B, terminal between A and B is drain. In case of a p MOSFET, so I will not put the arrow as of now. In case of a p MOSFET, but gate remains gate, let's put the gate and let's call this M2. If VSG, right, is greater than some VTH, right, let me call this VTH P, okay, then M2 is on, and lower voltage terminal between A and B is drain, right? So in essence, if we connect VDD on the top, right, if we connect VDD on the top and the current flows from the top to bottom, right, so this terminal becomes the drain. Now let me use a different color to differentiate. So this terminal becomes the drain, this terminal becomes the source, this remains the gate, right? So this is VDD. And if I go back to the cross section, the carriers are flowing from the higher potential terminal to the lower potential terminal, right? In case of an NMOS, the carriers were carriers for electrons, they were flowing from the lower potential to the higher potential, right? So in case of a p MOSFET, the carriers are flowing from the higher potential terminal to the lower potential terminal. Higher potential terminal is the source, and hence the arrow goes to the source and in the direction of current flow, right? So hence the arrow goes on the source in the direction of the current flow. So note that the direction of arrow points towards the inwards. It points inwards in case of a p MOSFET. In case of an N MOSFET, the arrow points outwards. Okay, fine, that's great. So let's proceed. So now that we know that uh, that the physical phenomena, the physical underlying phenomena, the physics behind the devices are almost identical, just that the carriers are reversed, and in essence everything is reversed. So whatever was the source in a MOSFET becomes a drain in a PMOSFET. Whatever was a drain in PMOSFET becomes a source in PMOSFET. The gates terminals are fine, but now in case of a NMOSFET, we require higher potential at the gate to turn on, higher potential in the gate with respect to the channel to turn on the device. In case of a PMOSFET, we want a lower potential in the gate than the channel to turn on the device, right? Okay. So in essence, the source should be at a higher potential than the gate in case of a PMOS, whereas the gate should be at a higher potential than the source in case of a NMOS. Similarly, without again deriving without deriving everything right from scratch, so what we will do is we will take the equations of the NMOSFET and modify it and make it a p-MOSFET equation, right? So let's write out the equations for the NMOSFET. So in case of so IDS is equal to half mu n Cox W by L VGS minus threshold voltage. I'm putting a subscript n because now we have both PMOS and an NMOS to deal with, so it's better to discern them. Whole square times 1 plus lambda VDS, right? So in case of an p-MOSFET, this will be the current flows from source to drain, so everything is reversed. So this becomes ISD, right, is equal to half mu p Cox. P is the mobility of the carrier. In this case, this is hole, times VSG minus VTPN whole square times 1 plus lambda VSD. Note that everything is identical, but for the fact that the polarities of the currents and the polarities of the voltages have gotten reversed. Okay. What is the equation? This is the equation in saturation. This is saturation. What is the linear current equation? The linear current equation is IDS is equal to mu n Cox W over L VGS minus threshold voltage times VDS minus half VDS squared. In case of a PMOS, it will be IST equal to mu p Cox times VSG minus threshold voltage times VSD minus half VSD squared, right? Okay. Another piece of information that we should I should tell you before we move on is that in the literature, when you see in some books, we tend to use these PMOS equations as negative. I mean, we tend to have negative VGS, negative VDS, negative threshold voltage in case of a PMOS equation. That is also fine, but the only key thing that we need to differentiate is the fact that sometimes in the literature, the threshold voltage is referred to as the voltage required on VGS, right? So in the literature, what is referred to is that sometimes threshold voltage is measured with respect to VGS and not VSG. So you might see negative VTHP in some textbooks, which is absolutely correct and absolutely fine. But in this course, what we will do is simplify our life, and we will say that we will be using the modulus of VTHP, and we will stick to, so that we will stick to this terminology of VSG wherever possible. Hence, what we need to do is to ensure that even if we are given a threshold voltage of negative, right, so we will make it positive by taking the modulus and use these current equations as we proceed. Okay, this is just to make our life easy, and we don't want to learn the current equations all over again for the PMOS, given that we have put in so much effort in understanding and the operation of an NMOS, right? So essentially, if we know how a NMOS works, what is the NMOS equation, current equation, we also know how the p-MOSFET will work, and we also know the p-MOSFET current equation, and just that we have to flip the terminals. Okay. So now, so this is as far as our terminologies are concerned, and as far as our currents and the voltages are concerned, absolute currents and voltages are concerned. But now it's time to move on to the incremental model also, right? So in an NMOS, what is the incremental model? So in an NMOS transistor, the incremental model is this. This is the source, this is the drain, this is the gate, right? And the current, the incremental current is GM times VGS, and the drain to source voltage is referred to as GDS, right? This is in case of an NMOS, and we refer to GM as dou ID dou VGS, and we get the multiple expressions that we get, right? Mu n C ox W over L times VGS minus threshold voltage, right? Or whatever we call it as mu n C ox twice mu n C ox W by L IDS. Okay. So what will be the corresponding incremental model in our case, in case of a PMOS? So let's do that. So in PMOS also we'll have a gate voltage, right? And we will have an incremental terminal, right? We'll have an incremental voltage control current source which is connected between the drain and the source terminals, and we should also have a incremental resistance connected between the drain and the source terminals. But now the way we have sketched it, right? Way we have sketched it in the actual sense, right? If I take you back to this diagram, the source was on top, right? The drain was at the bottom, right? So what I'm essentially pointing to is we need to establish which is the drain, which is the source, what is the direction of the current in the current source, right, and so on. So for that, what we need to do is we need to again go back to the drawing boards once again, and then and write out the equations, right? So let's say ISD is equal to half mu p Cox W by L VGS, or rather VSG, minus mod of VTP whole squared, right? So what will how should we define GM? If we want to define the GM as the same way as the NMOS transistor, because we don't want to get confused too much as to into thinking what should be the definition of GM, right? So let's do the usual thing first. So what will be if we define GM as dou ISD dou VSG, right? So what I'm saying is if we do dou ISD dou VSG, what should we get? We should get mu p Cox W by L VSG minus VTP, correct? Okay, so this will be the incremental current between the source and the drain with respect to VSG, correct? So let's say this is the source terminal, this is the drain terminal, right? So this will be, if we call this as GM, right, and we say that we'll keep the same current direction as in the MOSFET, because again we don't want to learn something new unnecessarily if we can draw a parallel between some things what we already know. So we don't want to change the incremental model, right? So we are trying to see how far we can get by without changing the incremental model and learning a brand new thing, right? So the current direction, if we keep it the same way, so what will be that current? The current is between source and drain, which is now GM times VSG, correct? So because note that GM in this case we are defining as dou ISD by dou VSG, correct? Okay, and this is the GDS. What will be the GDS? GDS we don't have too much of a problem, because in case of a GDS the current direction is not too much of an issue. In our NMOSFET model, GDS was lambda IDS. In case of a PMOSFET model, GDS will be this is lambda n, now this is lambda p IST, right? So this is what it is, right? But now you might turn around and tell me that this might be a bit more, I have been telling that this is we would like to keep these terminologies and everything same, but here I am using VGS, here I am using VSG. So this seems to be another extra thing to recall. So what we will do is we'll say that we'll keep this VGS only, right? We will not make this VSG, we'll keep this VGS. So let's keep this as VGS. Sorry. If we keep this as VGS, what do we need to do? We need to flip the terminal of the current source. So essentially this becomes pointing upwards, right? So in other words, this becomes our incremental model. This was our incremental model for our NMOSFET. This becomes our incremental model for the p-MOSFET, right? So note that there is a stark similarity between these two models, because as far as the incremental picture is concerned, we really don't care whether this is a NMOSFET or a p-MOSFET, because in the incremental sense everything is a linearized small signal equivalent of voltage control current sources and resistors and so on, right? So the similarities between these two models are: the gate remains as gate, GMVGS remains as GMVGS, GDS remains as GDS. There are two important distinctions, right? The important distinctions are that the source and the drain terminals we have expressed in the other way around. So in this case, in case of an N MOSFET, the source terminal was at the bottom. In this case, the source terminal, so let me use a different color. The source terminal was at the bottom. In this case, the source terminal is at the top, and the drain terminal in this case was at the top. Here, the drain terminal is at the bottom. And the third thing that is slightly different is the fact that the direction of the current source is also flipped. Now, if you want to make these exactly identical, we can still do that, right? So what we can still do is we basically can take the incremental drain to source model and flip it, right? So what I am essentially saying is this: the PMOS equivalent, incremental equivalent becomes, this is gate, we are marking this as drain and this as source, and this as GMVGS pointing upwards, correct? Why are we doing this? Because in the total picture, we generally tend to have the source on top, drain here, gate here. So these pictures look equivalent. Alternatively, if you are not comfortable, what you can also do is the following. What we can also do is keep the gate as gate, right? And let's say, just like in case of an NMOS, we had the drain on top and source on bottom. We can still do that, because note that here the current was flowing from, incremental current is still flowing from drain to source. We keep it as GMVGS, and this becomes GDS. So these two models are also identical, right? So there is absolutely no change between this model and this model. And the model in the bottom is exactly similar to the model of an NMOS transistor, right? But I mean, you can use either. There is no, I mean, we won't make any distinction if you choose to use the same model. But I personally prefer the model on the top, because there is a correlation between, there is a relation between the incremental model and the actual transistor. Because in the actual transistor we tend to put source on top, in the incremental model the source is on top. We tend to put the drain on the bottom in case of a PMOSFET. Here also the drain is at the bottom of the PMOSFET. So the visualization of the network becomes easier, right? So hence, in this course we would like to solve our problems using the model on the top. However, if it helps in your case, your personal case, you can choose to use either, right? So before we close today's lecture, let me just point out what can we gain from using a PMOSFET. So note that this was our incrementally, this was our common source amplifier, right, with the N MOSFET. This was grounded, this was source, this was GMVGS. I am ignoring GDS, right? I am ignoring GDS. But let's say, I mean, if I put GDS also, there is no harm. Say GDSN. Let me call this GMN. And this is RL. Okay. So what was the whole motivation behind search of PMOS? The whole motivation was to replace the RL with another transistor whose drain is connected to V naught, right? So this was V naught. So if we can use a PMOS, because the higher terminal voltage is now a source, then in principle this is possible to. So let's keep the bottom guy as is. If we replace the top guy, if we replace the RL with a PMOS transistor and we replace it with its PMOS equivalent, that is, we replace it with this structure, right? So what do we get? We get this is gate. This is gate of the PMOS. Let me call this GP, right? This is VGMP, VS, the GMP VGS, VGS. I should be using a different name, right? So let me call this GPSP, GMP VGP SP, and we have GDSP, right? Now if we connect these two here, correct, and if we incrementally short the source, just like we have been doing in case of the circuit on the left, then what do you think will be the resistance looking up, and what do you think will be the resistance looking down? The resistance looking up in this case can potentially be very high because we are looking at the drain of the transistor, right? And if we can if we look if in principle the resistance looking up into the drain of a transistor can be infinity, right? But we know that in presence of channel modulation it cannot be infinity, but it will be much higher than what we would have gotten if we used an RL. And in this case it is possible to probably get a common source amplifier whose gain is not limited by the quiescent drop across the load resistance, right? So we will start the next lecture from this position, and we will see how actually using a PMOS will help us breaking the trade-off between the quiescent drop and the achievable gain, right? Okay.